So I do want to start with the fundamentals, and then a little bit on judgment, and then finally go a bit further into the stability as we see it today. So, yeah, I know you're all brilliant out there, so I hope I don't insult anyone, but I get asked a lot of questions related to structural stability. I'm currently chairing ASC's TC3, who is in charge of Chapter C. I was on the original group that wrote the direct analysis method, so I've got a lot of background, I get a lot of email questions, and often it comes back to some very fundamental, so I tried to grab those and sort of highlight them for you. So the first one is just some really fundamentals. Force follows stiffness in the wet spaghetti test. But this is something that is often just overlooked, and it goes all the way back to your basic mechanics class. So let's start there. And that is, yeah, you're not interested in two-bar linkages per se, but extrapolate that in your mind to a structural system. But the easiest way to present it is with this little system. So on the left, we've got a connection, a bar, a connection, a bar, and a connection. And we're interested in knowing the total stiffness of that system. So it could be represented as 5 springs in series. And if you had some math, that's what you would actually calculate. But my point isn't for the math, but to really think about structural systems when they're in series and realize that if you apply that math, the system of the system stiffness is actually smaller, a lot smaller than the smallest of one of those individual stiffnesses. Right? So it really hurts when you put things in series. And so sometimes engineers will have this bracing set up, the bracing is all in series, and they've got a problem, they can't fix it, they call me up and well, what did you do? Well, we had it all in series. All right, what did you do? Then what we did is we added one more member in series, but this was a really stiff member, and it even made the problem worse. So here's a situation where you add material and you're going in the wrong direction. As long as you're putting more and more in series, you're making the problem worse and worse. Right? Now the counter to that is when things are in parallel. This is a much better universe to live in. So as a structural engineer, always sort of be asking yourself, especially in stability problems, am I helping the problem? Do I have my setup in parallel? So here are 3 springs now in parallel, 3 bars. Life is a lot better. In fact, the stiffness of this system is larger than the largest of any one of those, a lot larger. And anytime you add another component, you're adding more stiffness. So you're making the problem even better. So really focus on, do I have a problem here? And are they in series? And is there any way to switch from series to parallel? No. The other thing when things are, the force always has a load path. When they're in series, if one of those springs is a piece of wet spaghetti, you've lost the stiffness of the entire. But if you have things in parallel, if one goes soft, a connection starts to yield, there's an alternative load path, forces can redistribute. And so that's a really good thing to have on your side. So that's sort of my first. The second is sort of the basis of every structural analysis. What you've got is equilibrium. So the structural engineers, you're all cool with that. Some of the forces, some of the moments, you've done there a million times. The sister to that, which doesn't get a lot of attention, but are compatibility equations. So these are sort of the equivalent of the equilibrium, but they're in terms of displacements and rotation. So if you have a column and a beam connected to it, if that beam then rotates and it's a rigid connection, so does the column. All right? So these things all have to make sense. Now, fortunately, between the two of those, we have enough equations to solve any problem. Unfortunately, some of the equations are in forces and moments, and the others are in displacements and rotations. So we sort of have apples and oranges, and what allows you to move all to one side or the other are your constitutive equations, so your Hooke's law and all of that. So why do I bring that up? Well, a lot of you are using structural analysis software that can now do a geometric nonlinear second order P delta. And the only way it is doing that is by modifying either your equilibrium or your compatibility equations. Right, so it's the upper half. If they're being formulated, equilibrium and compatibility on the undeformed shape, you are not accounting for second order effects. If they're accounted for on the deformed shape, you are. All right. This bottom part is if you go even further and do a material nonlinear analysis. That is, you're going to account for yield and whatever. That can only be done through the constitutive relationships. So just again, I know it's just a wake-up call, but these are sort of the fundamentals that often get missed. Wait, how does the program account for? This is how it's doing it. Now, if we go all the way back to the oldest of the stability analysis, which we were mentioning, the mid-1700s, Euler looked at them. We could go through all the math. I just wanted to show you, though, if we actually looked at Euler's math, he started with equilibrium on the deformed shape. So he was already going to do second order. He had a buckle shape. He did equilibrium. He applied a moment curvature relationship, which is a constitutive relationship. This then provided him an opportunity to have a differential equation, which has been solved a million times before. This allowed him to actually solve it, but to actually get all the way down to the end on something we know, I squared EI over L squared, he needed to take one more step and apply compatibility and look at those boundary conditions. So once again, even the oldest stability analysis, equilibrium, compatibility, and a constitutive relationship. So those are your tools. Now, if you were to go to today's structural analysis software, so here's a SAP 2000 model, Dallas Cowboys Stadium, done by Walter P. Moore. But if you were to look underneath that structural analysis software, yeah, you'd find a lot of computer code, you'd find a lot of linear algebra. Keep digging, you will find equilibrium, compatibility, and that constitutive relationship. So it all comes down to those basics. Superposition, just a quick thought there, is always so tempting, but keep in mind, in order to superimpose effects, the system has to be behaving in a linear fashion. And many times, with respect to serviceability, you do have that condition, so you can apply superposition, but many times when you're looking at the ultimate strength, limit states design, and instability problem, you can't be using superposition. So have that in mind. And then, of course, we need some fundamentals on behavior. So this one I really enjoy showing. Gives us a little breather from the stability for a second, but you have probably seen this plot up here a million times before. It's a stress-strain plot for steel, comes up elastic, then we have a yield plateau, and then we have a long portion. What is often not understood is if we actually were to plot that to scale. So I've invited my friends, so when you live in central Pennsylvania where I live, you're either an Eagles fan or a Pittsburgh fan. I don't really follow football, but my daughters and wife are avid Steelers fans. So plus Pittsburgh's supposed to be the city of steel. So anyway, I'll use that. But here's how things are actually working. These Steelers fans are really sharp. They not only know football, but they also know structural steel. And if you take this spot right here, a little shaky, but that spot right there, and call that the 0 yard line, this spot right here, that break is the 1 yard line. Then we go 10 yards to this spot, which is the 10 yard line. And then to get to rupture, that's the Hail Mary, 90 more yards all the way over. All right, so steel has an amazing amount of ductility. But just because that ductility is there doesn't mean your connections are going to be ductile. All right, so you've got to be pretty sharp at proportioning your connections. We have in the past had fractured connections and lots of lessons learned, a lot of research done right here locally up at UT Austin, Professor Engelhardt. But you know, today these problems have been solved. So if you actually are designing steel connections according to the AISC rules, you will be able to develop lots of ductility, and you can see it in that connection, lots of yielding, lots of deformations without fracture, and that's what we're looking for. So, fun with designing steel. Steel has great strength to weight ratio, stiffness to weight ratio, but we do need to come in with a competitive price, and as a result, we end up with very slender structures. So it's not only the architect saying, oh, I love slenderness, but it's also, we're trying to be efficient with our material. And when you have that, slender members, systems, and cross-sections, you need to design for stability. So that's, so connections and stability are pretty much the game in structural steel. I'd like to break your world into two when it comes to buckling or designing for buckling. So on this block here, and we're going to go through this a couple of different times, On the horizontal axis is deflection, and on the vertical axis applied load. And we're going to look at two possibilities, and the first is bifurcation theory. This is pretty much what all of us came through whenever you were educated, 60s, 70s, 80s, into the 90s. And that was something was perfectly straight, nothing happened, and then suddenly, wham, it buckled. All right? And those are the differential equations you solved in life. But when we transitioned more recently in a design method that I'll talk about more deeply, we sort of had to assume something was not perfectly straight. There was a small amount of imperfection, and as you loaded, that imperfection started to grow, and eventually you would reach an instability. So two different schools, and it's the instability theory one that as we talk with people today, they're still wrestling with. So let's give that a try. So here's a couple of different possibilities. Here's a compression member. Let's say over on the right, we're testing this at Lehigh University, a big long structural steel column. We're squishing it, and we would have two schools. Now I've taken the structural member and I've sort of rotated it on its side, but if on the horizontal axis we were sort of monitoring lateral deflection of the column, on the vertical axis the applied load. Bifurcation would tell us we come all the way up, we hit Euler buckling, elastic flexural buckling, and off we go over. On the other hand, if we had some type of initial imperfection, we would load this thing up, and if we didn't get any yielding, it would sort of track the green curve, where that initial imperfection would start to grow. When it grew, the moments would grow. The moments grow bigger, more force, bigger moments, bigger deflection, and eventually we'll buckle the column. Of course, in reality, what happens is those moments grow, and between the combination of axial force, flexion, and a little bit of residual stress, we actually get inelastic flexural buckling. So it happens with a column. Here's a flexural member being subject to uniform bending. All right? And what we're going to monitor here, it's unbraced for quite some distance. We're going to look at lateral torsional buckling. So here's this point here, and as we apply these moments, if the member is perfectly straight, moment, and then suddenly we've got elastic LTV. If the member has any small, and they're real, initial imperfection out of plane, we get minor axis bending, not much, more moment, not much, and then suddenly out of plane, the moments start to grow. As we apply more major axis moment, we get more minor axis moment, more twist, some yielding, and eventually we get either elastic or inelastic lateral torsional buckling. Again, two schools, the bifurcation school and the instability school. This goes all the way to structural systems. All right, so if we have a structural system like this one here, we put some load on it, we could say, no, nothing happens, and suddenly the system buckles. But in reality, even if we don't have an initial imperfection, even if the system is non-symmetric, it will start to lean. And the second it starts to lean, we'll get some deflection laterally, we may pick up some yielding, and eventually we'll reach an inelastic limit point. So more axial force, more bending moment, more deflections, yielding, the whole system is coming apart. Right? Two schools. Now, the key to the second school in sort of understanding these green and blue curves is the stability analysis that you have to do. Right? It's got to include deformation, so you have to be doing equilibrium on the deformed shape. Critical. You have to have some type of disturbance. If the system is perfectly symmetric, you need to include some initial geometric imperfection. And there's going to be a loss, most likely due to yielding, that could be accentuated by the presence of residual stresses. So these things are hurting you. Now, if you also go back into 1980, Jerry Iflin and Charles Bernstein wrote a nice AIC report, and they went through and looked at all the different possibilities on what may cause a frame instability. And it was really between our knowledge, the group of us on TC10 and AIC, and Iflin and Bernstein's report that we wrote in 2005, the chapter C as you see it today, especially that front matter. So right up at the beginning, there's what I would call AIC's Big Five. And what are they? Your analysis must consider, your stability analysis must consider all pertinent deformations, equilibrium on the deformed shape, initial geometric imperfections, loss in stiffness due to yielding, and variation. And variation would be how you're capturing this with an omega or a feed factor. So again, just some background on how we got to those Big Five. and why they're so important to a stability analysis. All right, so much for the fundamentals. Let's keep rocking here. Judgment. All right, so this, I'm preaching to the choir here. You are structural engineers, and so nobody knows more about judgment. But the one thing I would like to say as an academic is please continue to embrace every opportunity. What makes you a structural engineer is that you are employing judgment. Don't let computer software or whatever overtake you. Let it inform your judgment, but you are in the end. So, embrace it. It's going to be constantly developed and constantly questioned. What were the assumptions? Am I satisfying equilibrium and compatibility? Have conversations with your colleagues about the structural designs that you're doing. All right? Just don't throw it in the RAM, get it out, put it on a drawing, send it out. At some point or another, have a conversation with your colleagues about the load paths. How is the load moving through that structural system? If it were to fail, we know you designed it so it wouldn't. But if it were to fail, where would it fail? What are the potential failure modes? Plot deformed shapes and moment diagrams, perform what-if scenarios. A column gets blown out, a connection fails. How are the forces redistributed? Right? And then finally, just a little shout out, because there is quite a range of age in this room. The younger engineers, you have to be willing to be mentored. All right? You got that great education at college, but find a person or several people in your firm and let them mentor you. Ask lots of questions and let them have an opportunity to respond. To the older generation, make sure you're willing to be the mentee, all right, or the mentor. Help them out. And also, old generation, don't stop. You don't know it all. And I suspect at meetings like this, you're having conversations amongst peers on how your structural analysis and performance and designs could be improved. So keep the conversation going, both the mentor and the mentee. Be both. All right, let's get into designing for structural stability. First, just a note, I have the pleasure of serving on all three of the specification committees for AISC, AISI, and the Aluminum Code. And a few years back, we did something really cool. Both AISI, aluminum went first, and we completely reformatted our specifications so they are aligned with AISC. So this is great news for a structural engineer. All three of these specifications now have the same chapter headings, and if you're looking for design for stability in all three of those specifications, it's in chapter C. And so finally, we've come together on that one. All right, let's talk about AISCs. I talked about the big five. AIC recognizes any rational method, but they really go into detail on two, the effective length method and the direct analysis method. This is why it's so important I was showing you those fundamentals. This is what I was after. The effective length method, which many of you have used and continue to use, is directly aligned with the bifurcation theory. On the other hand, in 2005, when we introduced the direct analysis method, it is not aligned with what you were educated with the bifurcation theory, but more this instability theory, this initial imperfection growing and yielding, and finally, what's being shown in that green curve, it's gradually an instability being reached. So that's important. Very important is both the effective length method and the direct analysis method are based on ultimate strength design, which means you need to account for second order effects. So a lot of structural engineers, when we introduced the direct analysis method, said, I'm sticking to effective length because I don't need to do a second order analysis. Not true. So it may be time for you to add a bumper sticker to your car. In the US, I don't know why only in the US, but people put a lot of bumper stickers on their cars. I showed this slide in an ARC night school. I just used Photoshop and created this bumper sticker and found a car and slapped it on the back. After that night, so I did it Monday night, Tuesday, all day, ARC headquarters was receiving requests from people. There were about 25 people on the line for the short course, calling in, asking for the bumper sticker. So it became a bit of a joke, but in reality, they actually went ahead and made bumper stickers. So if you're a true nerd, you will leave here with a bumper sticker. You don't have to put it on your car. That's right, true nerds. So put it on your laptop or give it, maybe for an anniversary gift. Equilibrium on the deformed shape. All right, quick discussion on the effective length method. The key here is we are using one factor, a K factor, one effective length factor per member to account for all of those big five. It's quite a chore for one coefficient to do. All right? It works well. It's been around for 55 years. In fact, the Higgins Award that I received, Ted Higgins was the one that introduced it to AIC in the early 1960s. All right? But it can do it. But you've got to make sure you've got the correct K factor. All right? And so there's lots of methods for computing these, alignment charts, which come with a whole bunch of assumptions. So my students are like junkies. They see the alignment charts. Oh, I can do that. And they're using them. And then I sort of rain on their parades. Now read the commentary with the 25 assumptions, and they realize they're violating about 12 of them. Then you can go to a structural analysis software, which will do a buckling or eigenvalue analysis and back calculate K factors. But you've got to be very careful. Lightly loaded portions of the structures will have very high K factors, artificially high. So you may be providing a lot of structural stability where you don't need it. So you've got to be careful there. It all comes down to how confident you are in your K factors. And so there are some nice resources for K factors. Probably the best one is an ASC document, a book, if you will, that's still available today that Jerry Hajar and his colleagues put together. And I really encourage you at some point to try to find that. If you get the right K factor, you're going to get the correct compressive strength. Otherwise, who knows what you're going to get. So let's talk about the direct analysis method, the alternative to this. And here, the whole concept, actually, truth be told, we made a colossal mistake. We shouldn't have called it the direct analysis method. It's not an analysis method, it's a design method. All right? But what it's doing here, what we should have called it is the direct modeling. By directly modeling more and more of those big five, you get more and more simplifications in the design code. So that's what we are after with the direct analysis method. So what are they? They're the big five. Pertinent deformations, stiffness distribution in your system, initial imperfections, yielding, force distribution, force moment distribution relative to the stiffness changes. So that's what we were after. So in 2005, we came out with the first version of the direct analysis method, modeled the pertinent deformations, the applied loads, modeled the initial system imperfections, just the outer plumb of the structure, not the individual member imperfections. And make sure you have some account in there for the possibility of yielding, and that's where we came up with that 0.8 on top. All right. If you do that, you don't need to calculate a K factor. You can just use the umbrace length or use K equals 1. So there was a big advantage to that. It relieved you of not sleeping at night because you didn't know if you got the correct K factor or not. In 2016, we went a little bit further, and I'll provide a couple of examples here. But if you did everything that the direct analysis did, then you could go to Appendix 1, and it would permit you to also model the member imperfections. And if you did that, then you didn't have to use AIC's column curve. The analysis, it was rigorous, second order. You could actually design by the strength, the cross-section strength. That was a big step for us. So there's a trade-off. Here is AIC's interaction equation. In the denominator are the required axial force and moment. Denominator are the capacities. And what's happening here is, if we look over on the left, sort of a, let's see, whoops. There we go. So we look down here, it seemed like in going with the effective length of the direct analysis method to the advanced direct analysis method, we were artificially increasing the axial capacity of the column. In fact, we were, but in putting the requirements on the analysis to include initial on a plumb, 0.8 on TAW, initial member imperfections, we were actually also increasing the demands on the moment. So it was a trade-off. And as a result of this trade-off, you get very similar designs, but you've got several different options. This is sort of a sliding scale, working left to right. In the upper, how prescriptive or how much do you want to rely on the specification equations from more to less, and how much do you want to directly model from less to more? This is a pretty standard, simple, straightforward steel building. either the effective length method or the direct analysis method. The standard direct analysis method will give similar results and will work perfectly well. You just, again, if you're going to use the effective length method, make sure you're getting your K factors correct. Now things start to get ugly, all right? We have things like over on the airport there, in the airport terminal, the architects decided to get real creative with us and provide tree columns, all right? So I don't know about you on the right, a classroom with a tree column, but I don't know what the unbraced length is. I don't know what the unbraced length is. I definitely don't know what a K factor is for that mess. So here would be a situation in which I would want to drop back and design for the individual cross-section capacity and actually model the imperfections and use a more rigorous analysis. And if you talk to the engineers that did these, that's what they did. Another example is an arch. What's the K factor for the arch? I don't know. What's the unbraced length? Still don't know. All right. So here's an example, again, right up here in Texas, of Walter P. Moore and Associates, my good friend Larry Griffiths. They had a bunch of pedestrian bridge, and they had an unbraced arch that were going to support these. So they didn't know how to calculate the capacity, the axial strength of the arch. So they modeled both the member imperfections, so in between each one of the panel points, they put a little out of straightness of the arch. And then they took the entire arch and modeled it as a system imperfection, sort of leaning out of plane. And once they did that, they ran a very rigorous second-order analysis. They used their 0.8 on top. And now when they went to actually check the capacity of the arch, they just needed to use the cross-section strength of the arch. They didn't have to go to the interaction equation or anything like that. So they really were fortunate there. Again, so here I am up in central PA. Our coin is super high right now, but the structure doesn't know. All right, you're the engineer making the call on whether you use the effective length method, the direct analysis method, or what. An alternative to this, how am I okay for time? About another hour? Good. All right. So the alternative to both of these elastic methods is there are much more sophisticated methods available to you. Again, one more version of the direct analysis method, but here you go all in. All right, you actually model the material nonlinear behavior. So you're doing your second order, you're modeling your system, but you're actually accounting for the yielding and the residual stresses. Even though this sounds like rocket science and it is relatively new to the specification, many of you learned this as plastic design. All right, so this is just plastic design on steroids. This is a bit more than plastic design, but the real nice thing is it allows you to not have to use the specification equations. All of that is being accounted for in the analysis. So you've got a nice option there to just go beyond first yielding and actually get an actual limit state for that structure. Here is an example of, see if I can, get it? Here is an example of where this inelastic analysis was used. It's not used every day, but this is a building, upper left there, you can see it, that was on Harvard's campus, or is on Harvard's campus. And if you look through the atrium, you can see another smaller building. There we go. You can see that smaller building in the background. That was the sort of the senior administrator's building, and they had a beautiful view of the Charles River. And they weren't too excited about the business school building this building in front of them, so they had a requirement that they had to see the Charles River. They were paying the bill. So what the architect did is built this giant atrium. They wanted it to be column-free, but the engineers were like, oh man, I don't want to do that because I'm going to have to make those upper 4 stories some giant bridge. That's going to get too expensive. So where they landed on were these ladder columns. And that's what's being shown in the background. Here we are in the atrium. These things right here. These things are very heavy W14 shapes. And what they've done is gone in and they've cut the web out of them. All right? So we're looking from, at the side of these things with no massive W shapes with no webs. Does not qualify for your AISC column curve, as you're aware. So they went forward and they used the Appendix 1 inelastic analysis to design those columns. So it's a real clever use there. Another area where inelastic analysis is being much more heavily used is that's in seismic. So if you go out to the West Coast especially, but if you actually go back a few years, it started with pushover analyses. All right? And those pushover analyses have now moved to doing full nonlinear time history analysis. And what does that mean when I do a full nonlinear time history analysis? Well, an earthquake is, say, 25 seconds long. We have to use a time step of about 100th of a second. So that's 2,500 nonlinear, both material and second order analysis that have to be performed during that earthquake period. And you have to look at known earthquakes. So these guys are all in, but today's computer hardware, it's being done on laptops, all right, and using structural analysis software like Perform 3D. So they can do it, and they are doing it. Now the rules for that, though, aren't really clear. So AISC has put together a task group that will be coming out with a new appendix to AIS 341 that's going to have one consistent set of rules on how to do these full nonlinear time history analysis in steel design. So something forthcoming there in your seismic code. That same group is also looking at how to better sort of dovetail the direct analysis method with the seismic provisions. So we've got some work going on there. Here's an example of that advanced analysis stuff, inelastic being used. My good friend Jim Malley, who's an engineer at Degenkolb, had a structural building here in Oakland on the left, and they needed to retrofit the building to make it hold up more modern day earthquake loads. So they looked at a lot of different possibilities, changing the connections throughout the building and the like, and where they landed on were at least exploring the use of these viscous dampers, and they would actually use them. Now, if I just have 1 minute, I can just tell, I just sort of, it cracks me up to think that somewhere in this building, upper floor, which has a beautiful view out into Oakland, this is your office. And then Jim Malley comes in and tells you, we're going to put a diagonal right through your beautiful window. Right? That's how you see the world out there. But you can almost imagine the way Jim Malley said it. He says, we're going to put the diagonals up in the office person said, ooh, that's going to obstruct my view. And Jim says, oh no, you got this all wrong. Think about it. During an earthquake, this building's going to be moving back and forth. That viscous damper is going to be pumping, and you're going to be sitting there watching it. It's going to be awesome. And then the office person says, oh, geez, really? And Jim says, yeah. You know what? I'm going to give you 2. I don't know if that's actually how it played out. Structural engineering, right? But that's what they actually went for. And this is their time history analysis. Again, a full nonlinear time history analysis that they used. On the left, they compared the structure with dampers. On the right, without. And what you'll start to see, now we're really into the body of the earthquake. On the right, we're getting quite a bit of these red spots. Those are connections being in significant distress. And we've got a front view of the building and a side view of the building, depending on which earthquake. On the left side, really not too much red going on. Those viscous dampers are really working hard and doing a good job of protecting the steel. So exciting times ahead. And this analysis, these types of analysis are more and more heavily being used, especially on the West Coast. Now, all of this is available to you in AISC's, in a design guide by AISC. So I would really encourage you, if you haven't yet, go in there, grab the design guide. Lots of examples provided and a good overview, a full enchilada of this direct analysis method. It's been available now, it's 15 years, and it really is a nice alternative to that effective length method. So to wrap up, I often get asked, I've spent my career at sort of trying to advance more and more higher levels of analysis in design, especially design in metal structures. I've often been asked, can you give us sort of what do you think? And I don't have a crystal ball, as you can see in the background here, but here are some thoughts. I do think, as far as component, connection modeling, all of that, viscous damping modeling, we know how to do that, and our computer software can do that. I think where you're going to see a more rapid change is actually the applied loads. They are going to be earth, wind, and fire. Earth seismic, as I was showing you before, but not tsunami, avalanche. All of these things, non-linear. You put the load on, and then you run your analysis. Now the load is actually going to be dynamic. Wind. All right, we go up and we do these wind tunnel tests. We have all the wind data, the distribution, time history on what pressures were on the side of that building. Take that envelope and then run it in your structural analysis. And of course, fire. There is not any more of a nonlinear problem than fire. The fire breaks out in one area, members start to soften, lose stiffness, those forces redistribute in the structure. There's a lot of redistribution going on in a fire. This one was sort of fun, at least for me to think about. Future speeds of computers are going to make sophisticated nonlinear analysis much more applicable. But you know, in 1989, up at Cornell, we were doing all of these analysis during my Ph.D. program. And we were dreaming about the year 2020 when you all would have the speeds that you actually have. Because we were convinced you'd all be doing full nonlinear time history analysis. What we didn't realize is what a lot of you did, and that is when you increase the speed of your computer by at least a factor of 1,000, if not more, compared to what we had in the late 80s. What you decided to do, instead of going more sophisticated analysis, is you decided to go from looking at 30 or 40 load combinations, which more senior people in the room knew how to do. They would say, I'm not going to look at a million different load combinations. I know the ones that I can control, and that's what I'm going to design for. Today, it seems like there's a little turning off the brain and letting the computer look at 300 to 500 different load combinations. Let it worry about it so I don't have to. All right? I get it. You know, that's okay. But are you really in the future going to let 3,000 or 4,000 load combinations look at? At some point, there's going to be the flashover in which you'll move from looking at load combinations to using more and more sophisticated analysis. So that could be exciting. And then there's all kinds of opportunities for virtual reality, artificial intelligence, and the use of big data in structural engineering. If you look at mechanical engineering, my daughter is in biomedical engineering, all of these are being used quite heavily. We are still pretty much old school 1980 sort of approach to things. It's doing the trick. I'm not saying change, but there must be an opportunity. You all are running structural analysis of certain designs. What would happen if we had a collective pool? So the next time I had to look at a building with viscous dampers, I could look at what the Dayton Cold engineer stated, what did they learn. So big data really has an opportunity here. So that's sort of my presentation. I try to emphasize to you the fundamentals and how they should be impacting your intuition. We do try our best to make sure you learn them during education, but to continue to take on night school courses, PDHs and the like. When you approach codes and specifications and design guides, constantly go back to your fundamentals. Wait, does this even satisfy equilibrium? A lot of deformed shapes every once in a while. Computer analysis, I'm a computer guy. I write software, but I'm telling you, don't let it control you. Let it inform you. Right? So that's important. And then, of course, you and your colleagues' experiences are incredibly valuable. But it's you and your colleagues. Have some conversations. So let these fundamentals, let all of these things guide your judgment, not replace it. So it's been a pleasure speaking with you. I hope I stayed fairly close to time. All right. Okay, very good. So thank you very much.